Okay, but yeah, you came up with the right thing. Work is force times distance. The only thing is, though, when you guys learned it back in general science, you had a constant force over a distance. We are now going to have a force that varies. Our force is not going to stay constant anymore. So that created some issues. But before we go to that particular issue, I need to do a couple checks. What are the units we use to represent work? Because I always thought they were very strange units. Joules, which is actually what times what, though?
Newtons times meters.
Yes. Newtons times meters, or another word, Newton meter, but we call it joules. Okay, the one that bugs me, I guess, more because we use it all the time. What if you're not metric? What measures force? Pounds. What measures distance? Feet. Yeah, and when we usually reverse it, a foot-pound. I just always seem like a very bizarre unit, a foot-pound.
What do they call that? They kind of name?
They call it a foot-pound. How many foot-pounds of force? Or that's what it is. So I always just, that seems like a strange concept. Okay, so right now, you guys know that if I tell you that you push on, something's pushing with 20 pounds of force and it moves something a distance of 10 feet, how much work was done? What do? You multiply them, 20 times 10, and you get 200 what? You get 200 foot-pounds of work was accomplished. Okay, but here comes our problem. We aren't going to have a constant 20 pounds of force. You're going to have some force that pushed for a certain distance, but then maybe you get a different force that pushed for a different distance, and then another force, so we got force 1 here. No, you cannot lock up. I don't need to stall today. Force 2, force 3. We got different forces doing different distances. How do I figure this out?
Different equation.
Well, it's still force times distance, but my force is varying. So I'm going to come up with a function to represent how the force is changing. So the force is now going to be a function that represents with a variable in it so that it can change as we move. And my distances are just how much, if this is a number line, this is how much my x-coordinates are changing. So my x-coordinate changed from here as x1 to x2. What do we call the change in x-coordinates? Delta x. But here in calculus, well, we've been calling delta x, changing it to dx. And so we actually were changing that to force times dx. And then I need to sum up all these different little sections of work that I've done, all these different force times distances. And I integrate it by summing up them all up. And so, yes, work is actually the integration from A to B, where A is your starting point and B is your ending point of your distances. And you integrate your force function times dx. That's your function, but we work with.
When you ask for the 2 common units of measure for wood, do you want joules?
Joules and foot-pound, yes. Okay, so here we go with my awesome drawing skills. Okay, yeah, this is a well. Woo! You got it! That's pretty unusual. Okay, and hanging down here, of course, is the bucket so we can get water out of our well. And yes, I should have a crank and a handle and so we can crank and the whole bit. Okay, it's actually wrapped around. I should have it wrapped around. The rope wraps around as you pump it up and all that good stuff. Okay, so yes, it's a well. The well is 40 feet deep. The bucket weighs 30 pounds when it's full. So that's an important piece of information. However, your bucket has a leak. There's a hole in it.
For a well.
Okay, so it loses 1/4 pound of water for each foot it's raised. It's on a motorized crank. It's a cut. We know. I just steal the problems, okay? You want to argue the physics of it all, you go argue with Mr. Gilbert.
There's no arguing.
There's no arguing, you'll just ask us a question. Another question.
Well,
Hey, I want to know how much work will it take to raise it to ground level? I'm not worried about that extra little distance. I just want to get it back to ground level here. Okay, so the formula I gave you isn't particularly useful. You need a formula for the force.
It drops -3. Yeah, -1.
Okay, because I'm losing X is going to be then my
30 minus 140.
but X, if we're doing dx, X is your distance it's traveling. So aren't you losing a 1/4 pound for every foot it comes up? So yeah, I agree. You're losing a 1/4 your X, but from what? What are you starting with?
30.
Yeah, you're starting with a full bucket, so you're starting with 30 pounds. And you're losing a 1/4 pound times the distance it travels. So there's your function. And then what does it say we should do with it? We should integrate it from...
-40 to 0.
You could do -40 to 0. They'll actually just do 0 to 40, yeah. But it will still come out correctly if you do it -40 to 0. So, but yeah, you can just do 0 to 40 if we're going to raise it that much distance. And so then you simply, that one actually would be easy to do by hand. But on these, I believe I have allowed you to use your calculator. So if I integrate that, that's going to become what? Or actually, you wouldn't know. Anybody want to guess? It's a really round number.
200.
Too low. 1,000. You're going to have done 1,000 foot-pounds of work. And shoot, I don't remember it. You have a problem on there. I hope I didn't kill it. I don't think I did. Where it then has you figure out how much horsepower that is in a motor to do that much work. And it tells you how many foot-pounds are in 1 horsepower. And I don't remember that number off the top of my head. But it's in a problem you're going to do. It's going to tell you that. So you can divide by however many foot-pounds it takes for a horsepower and figure out how many horsepower of engine you need to get that done if you were pumping it or something. You actually have some problems where you're going to pump water out of things. Okay. I'm going to do all 3 kinds of problems, and if I have time, I'm going to come back and do a second one like this. But I want to make sure I do the 3 kinds of problems first. So that's a basic lifting problem. You're lifting something up. You're going to have some cranes lifting buckets of sand, and there's sand that's falling out of the big scoop of sand that you're lifting, that type of thing. So you're going to have some problems like that. Okay. Yeah, second kind of problem that these work with is spring problems. You ever done springs before? Okay. Okay, specifically, springs follow what is known as Hooke's law. Hooke was a famous scientist / mathematician, more scientist, and he came up with a formula for how, some springs have lots of stretch and give. Some springs are very tight and they don't stretch easily. They take more force to get them to stretch or compress. This law works whether you're compressing the spring or stretching the spring. It's the same thing. He proved that to be true. And it's actually really quite simple. He figured out the amount of force it's going to take to change the length of your spring. He wrote it as K times X, where K is what's known as the spring constant. And I'll explain that better in a second. and x is the distance you are stretching or compressing.
Does this go in our journal under Hooke's law?
I'm pretty sure it would go under Hooke's law, yes.
I don't know if there's a
Okay, no, this is it. Okay, you have to figure out, before you can work any problem, you have to figure out what the spring constant is. The spring constant determines how stiff that spring is. The more force it takes, the stiffer it is, the more force it's going to take to move it. K is going to be a bigger number. If it's a really easy spring, then K is not going to be a very big number. Okay, so let me give you here, every time you work spring problems, you have to be sure you know what the natural length is. What do they mean by natural length?
how long is it not stretched?
Yeah, if it's just sitting there unstretched or compressed and just sitting there, what's its normal length? Because you have to measure everything off natural length. That's really important. So in this case, I'm telling you, you have a spring here whose natural length is 1 meter. Okay? It takes an 8 Newton force to stretch it to 3 meters. And I should say to a length, stretch it a length of 3 meters. Okay. My question to you is, how much work is required to stretch it from 2 meters to 4 meters? Okay. First thing you need to do is you got to figure out what the spring constant is. First thing, you got to find K before you can set up the problem to be solved. So you have to have a situation, they have to have told you the amount of force it took and the amount of length it got so that you can solve for K. You're just going to do the quick little algebra off to the side here. Okay, what is the force they gave me and a distance I know it stretched? Okay, an 8 Newton force. K is what I'm out to find. And I actually stretched it how far? 2, because I went from 1 to 3. So that's a 2 meter change is what you're looking at. And so therefore K is a really difficult 4. Ooh, that was tough. Okay, so then I'm going to set up an integration then. Our work, to find work, our formula says do the force function times dx. Okay, so in our case, our force function is Hooke's law. So I now know this is 4x is my function. That's the beauty of Hooke's law. You never have to hunt this function. It's just whatever number x. Okay, now here's the kicker. What am I integrating between? If I want to know what it takes to stretch it from 2 meters to 4 meters, how far are those from 1 meter? From 1 meter to 2 meters, that's already got a 1 meter stretch. And so from 4 meters to 1 meter, that's a 3 meters. These are from measured off a natural length. How much are you stretching it from natural length? That's the kicker. That's where people mess these up. And then, yes, super simple integration, and we can solve it. In fact, we could even do this one by hand. 2x squared from 1 to 3. 18 minus 2 would be 16 what? Joules. I was doing metric this time, yes. So it'll take 16 joules of work to do that. Okay. So that was spring ones. They usually like spring ones because spring ones are easy. Okay, the third kind in 7 minutes. Pumping water out of a tank, yeah. This is where it gets trickier. And this is where, oh man, I don't know if I'm, okay. We'll give you the basic premise. We may not get the last one done here, because it's the trickiest one. Okay, we're going to start with a nice rectangular tank. You wish all tanks were rectangular that you were going to pump water out of.
Actually, it's very, inefficient. That's cylinders.
Oh, you're doing cylinders and cones, yeah. More, way more common, but it could be a swimming pool, your fish tank,
I don't have fish.
giant fish tank.
Keep them in a pot.
Giant square pond.
Yeah, you dug a perfectly rectangular pond.
That actually would be a bad idea.
Actually, how deep is this water supposed to be? I guess it doesn't matter, okay. All right.
Sure, there's a drink on there,
Okay, that'll work.
That's also.
Okay, here's the surface of the water. Kind of, sort of, Okay, so I want to know how much work is it going to take to pump this water out of this tank? And it's an 8-foot tall tank. It's 12 feet long. And it is 6 feet wide. Okay. All right. Back when we did the water, lifting the bucket out of the well, what did we have to know about the water? What did they tell you about that water? Back one more. They told you the bucket was, they told you the water, you were losing 1/4 of a pound. They told you it was 30 pounds of water. You got to know the weight of water.
Is that one?
Okay. There is a known fact, and unless told otherwise, assuming you're using fresh water. Okay. The weight, it's called the weight density of water. Have you ever done that before somewhere in science land? So, weight density of water, and it's written, it's the letter rho. It actually looks like a P, but it's actually the Greek letter rho. Okay, so that's the weight density of water. If you are in feet and pounds kind of units, it's 62.4 pounds per cubic foot of water. If you have a cubic foot of water, it's going to weigh 62.4 pounds. Okay. If you're in metric, then it's 9,810 newtons per cubic meter.
A cubic foot is 62.4 pounds.
Yeah, I know that. I kind of
That
looked
doesn't
at
seem
too.
right.
Yeah.
Seems a little heavy.
You think? I swear it's out of every book direct, and every book uses the same one. So yeah, that's how heavy it is.
Is it fresh water? Like, what is the difference?
That's because salt water is less. Salt water has more buoyancy. But if it's salt lake, it may. I don't remember. You have a saltwater problem somewhere, and either today or next time when we're doing water, somewhere we'll hit salt water. Okay, so how do you figure this out? How do I figure out? I got to know how much this water weighs. Okay, what you have to do is you think of it when it pumps it out. Think of it like there's a little tiny thin layer up here. You're going to pump out little thin layers of water. You're taking out this thin layer and the next thin layer and the next thin layer, and that thin layer, its thickness is, it's a thickness of dx. Just like when we did our shells and disc methods, we had the thickness was dx. Yeah, I know my time is over, but I don't want to stop. So it's going to run long here. So you're talking about that little thickness you're pumping up. Okay. So the thickness we got covered. I need the volume of the thing, don't I? Because it's per cubic foot. Okay, so how do you get volume of a rectangle? Length times width times height. Okay, so we're going to have to do, we got height is dx. What's length? In this case, it's 12 by width is 6. So in other words, you're doing the area of it. I'm trying to get a general formula here. You're trying to do the area of it times the thickness. That'll give you the weight. That'll give you the volume of it. Then how do I get the weight of it? I would have to times by this weight density. So you times by rho. So you're gonna have to have all of that, and then where the integration comes in, we're doing all these little layers. So we're going to talk about what distance are we pumping them for each little layer. We're going to do all those little layers, and the weird thing is you have to call the top of the tank 0. So if I tell you this is, let's put it at the 3-foot line. That's 3 feet deep. If this is 3 feet deep, what am I actually integrating between? This would be, if 0 is here, this is how far down? If that's 3 feet deep, isn't this 5 feet total then? And the very bottom would be 8. So in this case, you would be integrating from 5 to 8. I'll write that. Okay, so the general formula, that's A to B. But in our case, for this particular problem, we would have done, okay, we're in feet, so our weight density would have been 62.4. In our case, our area is constant. Our length times width was 12 times 6 was our area. And then we would have to integrate it from the 5 to the 8 to get it out of there. Okay. And we're going to have to call it there. You can't do cones and you could do cylinders, you can't do cones. Can't do cones.